Good afternoon, everyone, and welcome to our seminar. I think I know almost everyone here, but if not, my name is Jana Otterbacher, and I'm from the School of Pure and Applied Sciences, the Cyprus Center for Algorithmic Transparency, CyCAT. And today we're very lucky to have with us Professor Tsvi Kuflik from the University of Haifa in Israel. Tsvika is actually a longtime friend and collaborator of our university. He's a full professor at Haifa, and just to say a few words about his background, he has quite a lot of practical experience beyond his academic experience as a software developer, team leader, and project manager for about 20 years. I just mentioned that because it's not that common to see an academic with that amount of practical experience, that's for sure. As you'll see, he has a lot of different interests, from user interfaces, ubiquitous computing environments, and another one of his interests, which is where we have collaborated the most with him here at Open University, is in the area of algorithmic transparency. How to make systems that apply artificial intelligence techniques understandable to their users. So without any more delay, I'm very happy to introduce Tsvika, and the floor is yours.
Thanks, Jana, and hello, everybody. And I'm happy to be here once more, because the work that is being presented here, actually, it's an evolution of work that was started quite some time ago in collaboration in the framework of the CyCAT project, where Avital began her academic career as a master's student, and then now a PhD student going to graduate hopefully in the near future. And the work is being presented simply as a follow-up on what we did before. And actually, this is one of the main parts of Avital's research. And some of the material might be well known, but we will go through it anyhow. So when we are looking at the different terms that now are surrounding us and appear in different contexts and different scenarios, so we get to learn about robotics and neural networks and deep learning and cloud computing and computer vision and natural language processing, big data, speech recognition, and we can go on and on and on and on. There are many, many, many terms that relate to computerized applications and applications where AI is involved. And if we are looking at everyday lives, we see Siri, and we see Hey Google, and we see Waze, and smart glasses, and various collaborative robots. Everything is now available to us on a daily basis. Behind all these terms and nice applications, there are algorithms. And there are algorithms that are actually driven by artificial intelligence that makes them a little bit more complicated and hard to understand. So let us start from the very beginning. Let us take a look at what we call an algorithmic system and go from there. So we can see a very simple illustration of what we call an algorithmic system model that mainly involves artificial intelligence or machine learning techniques within it. And it has several components. It has the training data, the algorithmic model itself, third parties, input and output. And let's take a look at each and every component first. So the algorithmic model is the core of this system, and is simply a computer program that implements a very complicated algorithm that actually, after being trained and configured, transform the input into some kind of an output. So eventually it performs a reasoning process about the input and provide an output that may be a decision, a recommendation, a list of pieces of information, ranked or not. Then there is the training data. The training data is the core part of this of such systems, because the algorithmic model is an algorithmic model. It does whatever it is designed to do, but it is based on a training data that is used to train, to identify various patterns, various behaviors, various phenomena that the algorithm needs to identify, and then using the input, take a decision according to what was learned from the training data. So the training data has an important role in the actions that the algorithm takes. However, in addition to the training data that is used to build the model or train the model, there are various aspects that are configurable. There is a configuration, various characteristics or parameters that can be set by the actual users, not the developers of the algorithm, but the users, that may define or control the behavior of the system. Then, once we have an algorithm model that has been trained, configured by its users, then it gets an input data and can decide whether to provide some credit card to an applicant, provide some recommendations about a medical treatment, whether to hire an employee or not, whether to release a prisoner, assuming that he will not get back to crime anymore, and other aspects. Finally, there is the output that is actually impacted by all the previous steps. The algorithm that has been trained, configured, the input data that has been provided, and eventually there is an output. There is a result of the computational process which has been performed. So now we have seen the schematic and simple description or illustration of an algorithmic system. Let us take a look and see who are the stakeholders of such a system, who may impact or be impacted by the system. So the first may be the developers. They are developing the system, they are testing it, they are making sure that there are no bugs, that it performs correctly, but they are doing the technical job. They make sure that all the components work, and we may note that implicitly or explicitly they impact the algorithm, they impact the behavior of the system, even without actually knowing it, and we'll touch it a little bit later. Then we have what we call observers. It's an abstract name to whoever may observe the behavior of the system, but without being affected or without taking any action using the system. It may be an auditor that maybe just watch and audit the behavior of the system, maybe a regulator that may define various regulations, rules that will impact the behavior of a system. Regulations, we can consider, for instance, GDPR. GDPR is an act that regulates behavior of computerized systems. So it's an example of a regulator that dictates how systems should behave, let people be forgotten, something about maintaining their privacy, etc. Then we have the user, and the user is a bit more complicated type of a stakeholder. First of all, it may be the operator. It may be the bank officer that actually activates a system that recommends whether to give a line of credit to an applicant. It may be the applicant himself or herself that is being impacted by the system's decision. So this is the end, maybe the end user, and it may be also the owner. So we are talking about the bank. The bank owns some system that does analysis of applications. So the bank itself is another stakeholder, and it's actually a user, even though the bank is an entity that does not use applications, but it's kind of more virtual. But bank management is another type of user. So we have seen the developer, we have seen the different users. What can the system be used for, and what can it be good for? And we can see a few daily examples, applications that are available and being used on a daily basis. This is not science fiction. These are daily tasks. We use automatic systems, we use algorithmic systems to filter job applications because we are getting many of those in response to any job that we try to fulfill, to any position we try to fulfill. Credit requests being analyzed by systems, whether automatically or within the, when a bank clerk activates such a system. There are judicial decisions, whether to let people go, release them on parole, whether they are on time or they should stay longer because they are suspect to be perform any kind of crime again when they're released. Medical decisions, treatment to patients. We can get systems to recommend or suggest doctors how to treat patients. Driving safety. I guess nowadays when we are driving, there are these systems that monitor our behavior, not allowing us or alerting us when we are deviating from a lane or when there is a risk of an accident. So we see them every day in our daily lives. We can see, for instance, a job filtering system. I mean, considering the training data, classically, these are CVs of applicants and the level of success, whether they succeeded in the job they fulfilled. So we have the CV and we have the outcome. We can train the system to link between a CV and a successful applicant. We have third parties, the users or the operators that configure the system according to companies' regulations or the company's constraints and policies. And then there are candidates' CVs that are being filtered by the system according to the patterns that were identified in the training data, controlled and configured by the system parameters, and eventually there is a recommendation whether to hire or not a candidate. We can look at credit request approval, same stuff. We see a database of applications and the level of success in paying back the loans. There is the bank policies that are being written and configured. And then there are the applications that are filtered and then finally a recommendation. And in a similar way, we can see medical decision support systems. Again, there are diseases, symptoms, actually treatments and prescriptions. There are some guidelines of the HMOs, any kind of medical guidelines, configuration and parameters that are being set. And there are the patient symptoms and the decision of the system or recommendation of the system how to deal with this specific patient. So we've seen three realistic scenarios where such systems may or actually operate. And here where the problem starts. These systems may be considered as black boxes. We don't know exactly how they work. We are not familiar with their reasoning process. We are hardly familiar with their training data or with their configuration. All we can see is that there is a system, there was an input, we got a recommendation or a suggestion, and basically that's it. Since nothing is clear, a byproduct of this opaqueness is the fact that the systems may be biased, may be discriminating, and we may not be aware of that. And this may happen due to various different reasons. And this is the issue that we try to see how we can address. So let us take a look at what may be the risks and biases in an algorithmic system after we are familiar with the system and in general with its components. Eventually, what we see is the output of a system. And this is where we may suspect that an algorithmic bias exists, where there is something that we think is wrong with the input. And we try to see what may be the reasons, what caused this kind of bias or inconsistency that we see. And we're talking about an algorithmic bias, we try to split the problem into different stages or different components. We try to look at the data that is being used, we try to look at the algorithmic process, and we try to look at the human aspect of this problem. So when we look at the data, we can when we look at the data, we can see that we have the input data and we have the training data. When you look at the training data is a set of examples, characteristics, and a result. And the large set of such examples is being used to train the algorithm to identify different patterns of behavior. And if this training data is biased, it does not match the reality, or it is not suited to the population or to the characteristics of the intended use, then the results may be biased. An interesting example might be the symptoms of a heart attack that were measured and identified mainly based on male patients. And when women with different symptoms were analyzed, nothing was identified, and such a phenomena was simply missed until it was realized that the female phenomena of female symptoms differ. So it might be that the training data does not fit the intended use. It might be also that the training data contained various information that may be irrelevant for the reasoning process, and thus an input data that contain irrelevant information may be interpreted wrongly and may cause bias or may cause discrimination, even though it was not intentional. So the training data is one aspect or one place where we should suspect or we should monitor, and the input data itself, we should ensure that it contains only relevant data for the reasoning process. Then there is the algorithmic process itself. When we are talking about programming, programming is done by humans. Humans come with their own cultural background, experience, personal biases. So even without being aware, we may induce biases into the program just by assuming assumptions based on our own experience and knowledge, which may be wrong in general or wrong in the case where the system is being planned to be used. When talking about human bias, again, we are talking about the developer. I just noted about that. We may be biased, and the result may be a program that is biased. And there are third parties that intentionally or unintentionally configure the system. If we take the medical scenario, for instance, some diseases may have a variety of solutions or variety of prescriptions that can be prescribed. Some of them are more expensive, some of them are less expensive. And if we are thinking about an HMO, an organization that is providing us some treatments or insurance company, they would like to reduce their expenses. So they will go for the least expensive solution, least expensive drug, least expensive treatment, not necessarily the best one. So configuration, this is a scenario where the configuration of the system may impact the results that may be suboptimal and sometimes may be harmful. So if we are mapping this kind of problem space, we can see that we have a variety of scenarios. So it might be something wrong with the training data, something wrong with the configuration, something wrong with the computational process itself, something wrong with the input data, and eventually the output may be something we don't expect or we don't want or we don't need. So our question is, okay, how we mitigate with these scenarios. And we see here the medical decision support systems example that we talked about, heart attack and females and males, so the disease symptoms. So the training data is actually disease and symptoms association and the recommended treatment, the reasoning done by the algorithm, health and HMO, health fund and medical insurance companies configure it and use regulations and apply whatever is needed to configure it. Eventually, there are patient symptoms and there is the treatment recommendations that is based on historical data and the configuration of the system. So the question is, how can we address these issues? Since we are talking about computational mechanism and computerized system and algorithmic system, we turn into formal fairness or formal treatment. What we call something that is formal can be verified, can be measured. So we try to look at measurables way to identify biases or to ensure that the system is not discriminating or fair. Somewhat similar to correctness or the correct actions of a program, but in this aspect, looking at an algorithmic systems and ensuring its fairness. So we would like to verify that the interpretation and application of rules is done in a consistent way and the same rules apply equally and uniformly to all users. So let's just have a few definitions, again, taken from law and sociology and introduced into computer science. And we see that we have what we call protected or sensitive attributes, that anything that has to do with confidential information about users that may not be relevant to a decision being taken in a specific cases. It may include race, gender, language, religion, political views, and more, as long as they are not related to the expected outcome. And they are sensitive. This is sensitive information because they are private and may be discriminating or used to discriminate ones. There are protected groups, minorities, groups of people that are qualified for special treatment, special protection by laws, policy, or any similar authorities. And there are proxy attributes. We talked about protected attributes, those that are directly may define a person as someone that may be discriminated. Proxy attributes are those that, even though they're not directly giving away a specific aspect of a user, they provide a hint. And this is something that if we consider, for instance, the address or the zip code, if we're considering places, then there are neighborhoods which are known to have certain kinds of populations, low income, different behaviors, immigrants. So a zip code or an address may provide a hint towards protected group or towards a specific race or gender. And these are things that also we need to be aware of and consider how to eliminate. Some definitions of fairness, again, taken from external sources and brought into algorithmic systems in recent years. The idea of individual fairness. It means that any two individuals that have similar characteristics should be treated similarly. And there is the issue of group fairness, where different or the property of demographics of people that are receiving a specific treatment, whether they are being accepted or rejected or allowed, should be something that should be proportional to their proportion in the population. So groups should be treated equally and not be discriminated against. When we are talking about formal solutions, we mean that there are solutions that may be applied, may be defined mathematically. So there is a formal way to define them. And what we try to do is actually, first of all, find out what we call examination methods, ways to find out whether a system is fair or unfair. And there are measurements or methods that we can take in order to improve. If we identify a system that it is unfair or discriminates, how can we mitigate this discrimination or unfairness? There are many tools that were developed for dealing with formal fairness, and this is what we'll try to look at. And again, when we try to look at the formal solutions, we try to look at two different aspects. First of all, we would like to know being able to identify biases, the existence of biases, the existence of discrimination. And for that, we use formal fairness examination methods that have, again, several aspects. The formalization, the discovery of discrimination and auditing. Or we can have mitigation methods, assuming that we identified some unfairness or some discrimination, we need to be able to deal with it. So let us look at fairness formalization. Fairness formalization means that we need to take an aspect of fairness and define it formally in a way that we can compute it. And we have here an example of group fairness, which is a statistical or demographic parity, or the property that the demographics of those receiving positive or negative classifications are identical to the demographics of the populations as a whole. And here there is a predictor that we have a predictor H from X to Y that achieves group fairness with a certain bias Q with respect to groups S and T that are part of the overall population. And there is a subset O of outcome if and only if the probability of the result for a specific member of the group is, and the difference between a different one is less than this threshold Q. So if we look at the formalities, we can see here a mathematical definition of what we call group parity. And if we implement it, we can go directly and implement a program that can introduce a set of inputs to an algorithmic system, get the output, and check whether the output fulfills this requirement or not. So we can go ahead and actually do that. Similarly, we can do it for individual fairness. Again, we can take, we define exactly the characteristics, and then we can have a set of cases, can apply the system to these specific cases and check. So we plan ahead of time. We prepare a set of test cases, and we check whether they fulfill the group fairness or the individual fairness or any other formal fairness measurement that we defined. So there is a way to mathematically ensure that the system is not discriminating or fair. However, it is not that simple, because in the literature, there is one paper that talks about 25 useful definitions of fairness. Another paper talks about 21 definitions and their politics. So there is no agreed upon terminology here. Still, there is a large variety, but there are ideas and there are ways to deal with them. And also there are some guidelines. If you'd like to ensure a specific type of fairness, okay, you may select or choose this on that. So there is a matrix, there is kind of a decision tree. So based on what you're interested in measuring or ensuring, you can select the right fairness measurement and apply it. Or you can select all of them, why not? And actually also IBM developed Fairness 365, a package that allows you actually to check and verify whether systems are discriminating or not. So we have the measurements, we defined the fairness formally. All we have to do is now to discover whether a system is fair or not. And it doesn't matter whether it is explicit or implicit. All we have to do and all we can do is to try and apply tools that use a carefully designed data set about individuals and group members and check the results and see whether they satisfy the fairness measurements that we define. And it can be done explicitly via automatically, whether it is explicitly or implicitly discriminating a user. When we're talking about discrimination discovery, generally we would like it to be carried out by the developers or the developing agency in order to ensure that the system that is being delivered is actually fair with respect to the intended use. However, since those systems may impact the general public, may impact people's lives, may impact people's welfare, we think that there is a need also for an independent evaluation, meaning auditing. So auditing actually is the process of analysis of the results of a system by an independent evaluator, independent observer. The tools and techniques probably are similar to those of discrimination discovery. The intention is to use a carefully crafted data set of cases where the input is provided and the expected fair output is known, and we try to see whether the system is performing correctly. But the point is that this is done by an external agency, whether some kind of a regulator or a free and independent agency that ensures that the system is fair. So the idea is the same, but doing it different. If everything is fine, that's great, but sometimes we find out that the system is unfair. And we've seen numerous examples. Classic examples is the image analysis of Google with the gorilla image, etc. So we would like to fix, in case we are getting into trouble, we would like to fix the problems. And fixing the problems is relatively straightforward. First of all, we need to ensure that the data set is representing, that it is not limited to a specific type or a specific group, that it does not discriminate, that it contains a balanced set of examples. So we simply either ensure that the set is balanced, or we are looking at the training data and we are removing attributes that are irrelevant the attributes, they are protected attributes or proxy attributes, as long as they are not relevant to the decision being taken, then they need to be removed from the data. So the reasoning process will not take them into account. Learning, we need to take into account the algorithm itself, whether it has been programmed, whether it has been programmed in a way that is biased. It is not that common when we are taking into account classical machine learning algorithms, because they are simply learning patterns from the data that is introduced. But if we are programming a specific decision support system, we are defining decision rules, then these rules that we define manually may be impacted by our own background and cultural biases. So also the algorithms themselves may need to be fixed. So this is another way of doing that. And there are also ways to discuss the issue of fairness learning. Modification of the learning algorithm is within process. Pre-processing is something that actually relates to the training data. So it's not exactly learning, and it might be post-processing is actually trying to balance the results or check the results. But I think that when talking about learning, even though the paper of Alessandro described 3 steps, the first one is actually relates to the data and not to the algorithm itself. Within process is the algorithm. Post-processing, again, is after the process. And there are some examples of how to do and what to do. Again, there were studies about how to reweighting or generate weight for training examples, removing prejudice or equalizing the odds of a result, so finalizing or finding the right probabilities. So finally, we are getting to a more comprehensive a model that basically this is the same basic system that we discussed. However, first of all, we are aware of the components of the system, the risks of biases which are embedded in each and every component, and possible steps that we may be needing to take in order to avoid or prevent, overcome biases in these systems. So the formalities are a way to ensure that computationally the system is fair. And the question that comes immediately after that, well, we ensure that the system is formally fair. Is it enough? And this is one of the main issues that we were addressed, and actually this is what Avital is actually working on or focusing, and this is the issue of user perception. It is not enough that the system is fair. The point is that we need a system to be perceived as a fair one, to be used and to be trusted. And this is something that really matters as well. So we ensure that the system is fair, but we need to ensure that it is also perceived as a fair one. And we are talking about subjective perception of the system, subjective perceptions of risks and biases. And it's very simple. Perceived bias is simply the difference or the inconsistency between the input and the output. It may be a result of a cognitive bias, a framing effect, the way that the information is presented. It may be something that has to do with the knowledge of the user about the domain, about the system, about the way it acts, it is activated. Simply diversity of the users. There is a great diversity with different opinions, different background, different knowledge, different beliefs. We are different. So we perceive things differently. And users' perception is something that we need to deal with. And to illustrate some stuff, we did a very, very simple experiment. Since we're in an academic environment, we ask students, would you like to get extra points, 10 points to your final grade? All you have to do is answer yes or no. The second system, and all you have to do is answer yes or no. They pressed, they selected, no one got anything to their final grade. And the question is it fair? The second system is the same actually, but there was an explanation. All you have to do is press yes or no as before, but there will be only one winner. If only one presses yes, this one wins. And again, you can press yes or no. So no one actually got the 10 points also on the second attempt. But we had 84 students in two different places playing this game with the system, some in Israel, some in Brazil. And with system 1, 72 out of the 84 wanted to get a 10%. No one got the points, and about 39 thought that the system was unfair. Well, they were willing to respond. The second system, only 27 pressed yes. Maybe they were tired, maybe they realized, maybe they tried, but again, nobody got the points, but very few, or much less, thought that the system is unfair. That may be attributed to the explanation that they got, at least partially. Maybe they were lazy, it's another opportunity. But this is something that illustrates a bit, kind of intuitively, the issue of perception. So when we are talking about perceived bias, it may impact the input that we provide to the system because we suspect that the system is unfair. So we try to trick it, we try to cheat it. So we are trying to manipulate the system to get the solution that we want, which is not necessarily what we need or what we deserve. And the perceived bias may be also impacted by the input and output correlation, which we tend to disagree about. So we have this possible characteristic, and we can take a look again at all this algorithmic system. Now we add to this diagram also the perceived bias, which is somehow related to the correlation or lack of correlation between the input and the expected output and our beliefs about the system. And again, everything is here. And again, the health recommender systems and patient symptoms and the recommended treatment. And here there is the user's perception on the input-output correlation and cognitive bias, and what may impact the user perception about the system's behavior. And this is something that is important because if we're talking about a physician, a doctor that actually consults a system for recommended treatment, the doctor may be suspicious about the system recommendations based on what may be inconsistency between the symptoms and the recommended treatment that may be a result of training data, configuration, or lack of knowledge of the user. The doctors they have a limited knowledge. Or the user, the impacted user, the patient, may be suggested a treatment and the patient may be suspicious about, well, do they want to save money? And they are offering me a less expensive treatment. So these are issues about perception of fairness. So we're talking about informal fairness, the perception, which is based on, it is basically subjective point of view related to morality, related to other aspects, but basically it is a subjective issue. And we are talking about, when we are talking, again, we are bringing in terminology from sociology, from legal sources. So we're talking about distributive fairness, the fairness perceptions of the perceived outcome and its distribution, whether it is a fair distribution with respect to the populations or to the input. There is a procedural fairness, whether the procedure itself has been perceived to be fair. The informational fairness, whether the process, whether the person that got the treatment got the right information. And there is interactional fairness, whether the perception of the person was treated nicely and fairly. And this is something when it is a system, it's not interpersonal relationships. So the interactional fairness is something that cannot be considered, cannot be taken into account. But the previous three may be relevant and important: the distributive fairness, procedural, and informational. And we will look into that a little bit. So we are talking about informal solutions. And again, we would like to suggest what we call examination methods and improvement methods. Examination, finding out whether the system is perceived to be unfair. And improvement, how can we mitigate wrong perception? So we have a fairness perception examination. This is quite simple. We'd like to understand the individual perception about input-output ratio, maybe the performance of the algorithmic procedure, the quality of personal treatment that the person got, expectations and explanations provided by the system to the users. So there are various aspects that can be considered and can be addressed. And in order to measure, we can use questionnaires, we can use interviews, we can apply statistical tests to questionnaires to figure out what people think about the behavior of the system. So these are classical human-computer interaction tools that we can apply in order to figure out whether the system is perceived to be fair. Similarly, like what we do, whether the system is useful, usable, etc. So we need to a little bit know what our users think about the system. Then we can think about how to improve the perception of the system. And here we need to be a bit careful. There is explainability, what we call explainability management. We can provide explanations, and we can provide explanations in different levels. When we are talking about the system, we can talk about systems that are white box and systems that are black box. White box means that the algorithms are tractable. We can follow the reasoning process, and we can, with a certain effort, understand the way the system performs. Black box explanation or black box system are systems that are based on classical or deep learning algorithms, where it is really hard to try and decipher the way the system works. So when we're talking about explainability, or we're talking about explained decision made by an algorithmic system, it is known from literature, from research, that providing explanations may increase the perception of transparency of a system, in turn may promote or enhance the trustworthiness or the belief that the system is trustworthy, and all in all contribute to the fairness, the perception of the fairness of the system. So explanations are an important aspect. When we talked about a white box explanation, we simply try to follow the reasoning process of the algorithm and try to abstract this reasoning process and explain how the system, from a given output through a specific process, application of rules, or a Bayesian reasoning, received or achieved a specific decision. And this is something that can be traced, since those simple machine learning algorithms are generally more transparent. Decision trees, decision rules, Bayesian networks, eventually there is a path that can be extracted and explained as a decision process. So this can be done. However, when we talk about a black box explanation, things are becoming much more challenging. And when we're talking about black box explanation, we may talk about model explanation, try to see how we can explain the behavior of the model, and outcome explanations, how we can simply explain the results. And one way of explaining the black box algorithms is actually getting a considerable number of recommendations or cases where we have the input and we have the output, and we can try and apply a classical white box machine learning algorithms into these cases and try to figure out whether we can train a white box algorithms based on the input and the resulting output to replicate the reasoning process. And if we are able to do that in high accuracy, we can actually replicate or explain the decision process using this white box algorithm that imitates the black box decision process that was followed. Another, a completely different aspect is certification, where a system gets a certificate, like the online payment mechanism that we got, like the VeriSign. We got an approval of an independent agency, independent authority, that the system is protecting our credit card data. It has been tested. It will not use our data or keep it or use it in a wrong way. So a fairness certification means that the system has been tested, verified, and it is certified based on some auditing process and externally. So there is an external trusted factor. So these are the two ways for dealing with fairness treatment. Now what we did is, after we completed this kind of analytical treatment and following this kind of reasoning about literature and trying to come up with the ideas, we did another experiment. And we created or simulated a job application process when there are two possible outputs. A recommended, okay, we are going to hire an applicant, or we are going to reject an application. And we had 5 different explanation styles: case-based, meaning somebody with this characteristic got these results; demographic-based, looking at the demographics of the applicant and giving an explanation; input and influence-based, meaning that because of this and this characteristic of the input, you were accepted or rejected; sensitivity-based, meaning you can change. If changing this characteristic, then the result might be changed; and there is certification. Simply there is a stamp. The system is certified for fairness, and you got the result from a certified system. And we got a couple of candidates. Candidates with good characteristics should have been accepted, and kind of somebody that is not that great candidate. And we try to see the perceptions of users about the system, how they evaluate the fairness of a system, how the explanations impact their perceived fairness, and the level of understanding of the results giving the explanations. Mechanical Turk, about 425 participants, and the results. So we had two types of results. Candidate was recommended by the system. The candidate was not recommended by the system. And we can see aspects of fairness, impact, and understanding. The scale was between -2 to 2. So 0 is neutral. And we can see that when the candidate was not recommended by the system was considered to be unfair. System was considered to be unfair. The sensitivity-based explanation seems to be the preferred one. It contributed a lot to understandability, and it had an impact on the decision, and the fairness level of the system was kind of neutral, almost neutral, a little bit negative, but almost neutral. This is the bold on the top. Looking at the bottom, we can see when the candidate was accepted, then almost every explanation contributed, had an impact, and the system was considered to be fair, besides the demographic, which somehow seems to be not that effective, not that contributing. And again, sensitivity would seem to be the best for understanding, while the impact certification, surprisingly, the certificate made an impact, and the certificate was considered best for the fairness perception. So these were quite interesting results. So the conclusions we already discussed. When there is a negative, system is considered to be unfair, and explanation help in understanding in general. So these are the two main results in our this type of study. When the result is negative, people are suspicious. When the results are positive, they are quite happy. Explanations do help and make an impact, but the situation may be also different. So to wrap up, when we're talking about algorithmic transparency, explainability promotes transparency. Transparency and explainability both promote the fairness perception of the system, and explanations are important. So we have wrapped up everything. We have the definition of the abstract description of an algorithmic system with their potential biases, two types of bias mitigations, formal and informal, and there is one issue to still consider, and this is the overall scope of the overall space. But before getting to the last slide, the question is, what is missing here? We talked about formal, we talked about informal. Is there anything missing here? Informal, we are talking about persuasion in a way. Does it sound suspicious? Okay, we'll go to this and then we'll get to it a bit later. If a system is fair formally and perceived to be fair, there's nothing to do. If a system is unfair formally but perceived fair, we need to deal with the formal fairness. If it is formally fair and perceived unfair, we need to deal with the perceptions. And if both, we need to deal with both sides. But the point is that we need first to ensure that the system is fair formally, because we don't want to mislead our users. This is an ethical issue. We would like to ensure that the users are getting a fair treatment and then test their perception. If they perceive the system to be fair, we are happy, we are done. If they are not perceiving the system fair, then we need to take care of their perception. So first of all, we need to ensure fairness. lack of discrimination, then we can take care of the perception, because we don't want to persuade people to believe or trust the system before it has been proven to be fair. So this is kind of the potential ethical issue that I was talking before. We have 3 papers that Avital actually published. We have another study, if you'll be interested, because time is up, but we have another study that we can discuss. But at the moment, if there are any questions, if there are any issues, so we are done. So this part is done. Now it's up to you. There is the last paper of Avital, which is a bit more complicated because it's dealt with a variety of issues, and it went into personality aspects and what type of explanations may fit what type of user or personality. We can go into that, you can take the paper or whatever. This is something, this is kind of an extra we can consider. So it's up to you.
Is it based on the mechanical Turk data?
Yep.
Okay.
Everything that we did, because we went to hundreds and thousands. Here we had 425 or whatever. There we had over 3,000 participants because we have like 72 cases. So we had a large number. Now Avital is working on another one, which actually replicates the previous one, the types of explanations versus personality. And she's now, interestingly enough, what we played here, we said, okay, there was a system that recommended blah, 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 blah. And now an idea came up, okay, let's test the recommendations by a human evaluator. And we want to see whether the user's perception will be different given the fact that the evaluation was made by a human evaluator versus the evaluations were made by the system. Because we know that there are differences between, so different perceptions of decisions made by human and decisions made by system. So we'd like to see in the same scenario, same characteristic, whether there will be a difference. So this is, now we are done with experiments and Avital is analyzing the results.